We're going to be talking about ionic bonding with polyatomic ions. So what is a polyatomic? So poly means many or more than one, and atomic is atoms. So we're dealing with many atoms put together in the form of an ion. These are naturally occurring, and they can be either cations or anions. And remember that a cation gives away valence electrons in order to bond, and an anion takes those valence electrons in order to bond. And the purpose of the giving and taking is to complete the octet rule and become stable in the valence shell. On the back side of your periodic table, on the upper left-hand corner in the chart that says common transition metals and polyatomic ions, this is where you're going to find the polyatomic ions that I'm going to be referring to. On this chart, there's only one cation listed, which is ammonium. So over here you have the positive cations and then the negative anions. So the ammonium is the very first cation listed, and you can see that it has many atoms. It has 1 nitrogen and 4 hydrogens and a positive symbol left over, so plus. If you just see a plus or a minus by itself, assume that it's the number 1, so plus 1. The rest of these positive ions are transition metals. So this is the only positive cation. The entire right-hand column in this box, negative ions, which are anions, these are all polyatomic anions. So we're going to be using a couple of these as an example. I'll use ammonium as an example, and I'll show you how to create an ionic bond with polyatomic ions. There's a couple of tricks to it. So I'm going to be using these as in your problems. All right, so let's start with the first problem. I'm using ammonium, and right off the bat, before I even create the compound, let's talk about naming protocol. Polyatomic ions get to keep their names. And that's if they are a cation or an anion, it doesn't matter. Compared to, say, an element on the front side of the periodic table, a monatomic ion, like oxygen becomes oxide, sulfur becomes sulfide, they didn't get to keep their names. So when you have a monatomic ion that's listed on the front side of the periodic table and it's an anion, you have to change the ending of that element to "ide." That is not the case with polyatomic ions. They get to keep their names. You have to make that distinction between monatomic and polyatomic ions. So right off the bat, I know that NH4 plus 1 has the name ammonium. So I'm going to name it. This is ammonium. Gets to keep its name. And the anion in this case is fluorine with a -1 charge. Fluorine is just a monatomic element on the periodic table, and because it's acting as an anion, instead of fluorine, it's fluoride. So again, the naming rules for monatomic ions stay, but polyatomic ions get to keep their names. So this is named ammonium fluoride. So what compound does it create? Well, ammonium has 1 electron to give away. And that's the only thing that I really need to be looking at. The fact that there's 4 hydrogens and 1 nitrogen doesn't really matter. It's a polyatomic ion that stays together, and you'll learn about how they're formed later. For now, all I really care about is that charge. So I have 1 electron to give away in ammonium, and fluorine just so happens to need 1 electron. So that 1 electron will transfer to fluorine, and the octet rule will be completed for everything involved. And I know that to be true because I reach 0 on my charges. And all you do is rewrite the compounds. There's ammonium, but without the charges. So you just stick them together. So it's the exact same thing as when you're dealing with monatomic ions when your charges cancel out. So NH4, and remember that 4 is a subscript or written down below, and I know that because that's exactly how it's written on this paper, as a subscript. Okay, the next option. Well, what if the charges don't cancel out when you're dealing with the polyatomic ion? So this is ammonium again, so I'll just name it really quick. So this is ammonium. Sulfur is a monatomic ion, so because it's acting as an anion, you change the ending of it to "ide." So this is sulfide. And then all I care about again are these charges. So +1 and -2. Well, sulfur needs 2 electrons, so the ammonium will transfer its 1 electron, but it's going to need another ammonium to transfer that 2nd electron. And when that happens, the octet rule has been completed, and I know that because I have a +2 on the cation side, +1, +2, -2 on the anion side, that equals 0, so I know the octet rule has been completed for all of the substances involved, whether it's a monatomic or polyatomic. And this is a little tricky, so this is going to be a little different from the first example. It took 1, 2 ammoniums to complete the octet rule for every 1 sulfur. So because it took 2 ammoniums, you write NH4, that's ammonium, and the trick is that you have to put it in parentheses. It took 2 of them, and I'm going to write the number 2 outside the parentheses. So remember that this subscript right here is the ratio of what it took to balance the charges, which is not the same as this subscript in here, which gets a little confusing. So the subscript 4 belongs to the hydrogen, just saying that there's 1 nitrogen and 4 hydrogens. And this subscript 2 tells you how many of that polyatomic ion you have to complete the octet rule. So it took 2 of them for every 1 sulfur. So the trick is that you use parentheses when there are multiple of a polyatomic ion. And you write it exactly how you see it. So you wouldn't try to multiply or add these numbers together. This number 2, again, is just a ratio of what it took to balance the octet rule. Okay, next one. Magnesium is just an element listed on the periodic table. It's a cation, so as far as the naming goes, it's just magnesium. And this PO4 3-, so that looks like a polyatomic ion, so I'm going to come over to my list. And these are alphabetical, and so find the P's right here. PO4 3- is called phosphate. Remember, polyatomic ions get to keep their names, so I'm going to call this phosphate. So this is magnesium phosphate. So how do I create the compound? Well, this is a 3-2 situation. Least common multiple between 3 and 2 is 6. So I'm going to add on to both sides until I get to 6. And you notice on the polyatomic ion, I wrote PO4 exactly the same way. I only care about the charge, which is the -3. I'm not going to do anything about that 4. You write them exactly how you see them on the paper. So +2 + 2 + 2, that's +6. Add that to -3 and -3, which is -6. My charges cancel out, so these 2 electrons will transfer to the phosphate. It needs 1 more, so it'll get transferred from the 2nd magnesium. The 2nd magnesium will transfer its next electron to the 2nd phosphate, and then these 2 electrons will complete the octet rule of that 2nd phosphate. So all the electrons has been distributed, octet rule has been completed. It took 1, 2, 3 magnesiums and 1, 2, and you notice that I'm not circling the charges, I'm just circling the PO4. It took 2 phosphates. So again, when there's multiple of a polyatomic ion, I'm going to use parentheses, so automatically I'm going to put PO4 in parentheses, and outside the parentheses you write the subscript that tells you how many phosphates you needed to complete the octet rule. So because there's 1, 2, you put a 2 there. Next example, iron 3. Well, iron 3 is a transition metal, and transition metals can take on multiple charges. So right off the bat, when I name this, I'm going to use iron Roman numeral 3. So iron Roman numeral 3. And then on the back side of the periodic table again, I see OH. Oftentimes students just think, oh, I'm going to name this oxygen hydrogen. Whenever you see multiple capital letters put together, it is a polyatomic ion. Immediately look on the back of your periodic table. The OH is right there. It has a -1 charge. It is called hydroxide. So this is iron 3 hydroxide. Again, polyatomic ions get to keep their names. So iron has 3 electrons to give away. It'll give 1 away to the hydroxide, but there's still 2 left over, so I'll add on 2 more hydroxides. So 1 electron here and 1 electron here. Iron had 3 electrons to give away. It took 1, 2, 3, -3 to accept those electrons. And so, again, the compound, the ionic compound, is just the ratio of what it took to complete the octet rule. It took 1 iron, and it took 1, 2, 3 hydroxides, which is a polyatomic ion, and I'm going to use parentheses because there are multiple of the polyatomic ions. So automatically, I'm going to put the OH, both capital letters, inside the parentheses, and the number 3 outside the parentheses because there are 1, 2, 3 of them. Last example, Pb is lead +2. Lead +2 is a transition metal that takes on multiple charges. So when I write the name, I'm going to write lead with the Roman numeral 2. So lead, Roman numeral 2. I know that because there's a 2 here. And then there's this funky thing. Again, when you see multiple capital letters pushed together, it is a polyatomic ion. Immediately look on the back side of your periodic table. So I'm going to look for C2H3O2, which is up at the top. It's called acetate. So this is led to acetate. Okay, so as far as dealing with this one, oftentimes students have a hard time with acetate because there are 3 elements here, but it doesn't matter. All I care about is this charge right here. So this acetate only wants to accept 1 electron to complete the octet rule. Lead has 2 to give away. So lead will give 1 of its electrons to acetate, but another acetate is going to have to come along to accept that other electron. So when that happens, lead has a +2 charge, meaning that it's going to give away 2 electrons. It took 1, 2 acetates, each with a -1 charge, to accept those electrons. The octet rule has been completed. I know that because I reached 0. And it took 1 lead and 1, 2 acetates to make that happen. So again, multiple of a polyatomic, immediately parentheses. C2H3O2 is acetate. And there are 2 of them. And that's it.